Hello, everyone. Good morning. This is Kalyan, Kalyan Saladi. I've been a software engineer at Meta for the last almost 8 years. Worked on production web services, production ML infrastructure, and right now in research infrastructure team. Before that, I was at VMware working on virtualization and scheduling. Back to Chris.
And I'm Chris. I've worked at Facebook since 2011. Sorry, Meta. There's going to be a lot of muscle memory in there. I've worked on products like Search, Instagram, Messenger. Also infrastructure. I ran the Instagram migration from AWS to Facebook Infra. Worked on a whole bunch of other acquisitions as well. WhatsApp, Anavo, Beat Games, a whole bunch you've never heard of. Most recently, I've been working on AI and machine learning. I started on our production inference setup, then to the production training setup, and now I specialize in research use cases. So what are we going to talk about? We're going to talk about 3 R's: RSC, results, and relationships. RSC, the Research SuperCluster. Well, this is the cluster that we set up to help our AI research teams better do their jobs. Has some unique problems. So I'm going to start by explaining a few of the problems. AI training is very, very different to regular production request response type services. I've worked on a bunch of those. AI training is like nothing I've ever worked on before. Usually, my response takes, a bad one takes 100 milliseconds. Well, a response from an AI training job might take a week. And it's very different to other batch job style workloads. It doesn't really work the same as MapReduce because the way training works has this gang scheduling mentality where all of the components have to work together. They have to work together to answer to run the training job. The cluster has to perform as one cohesive unit, as an orchestra for many days or weeks. You can kind of think of this like it isn't really a group of computers. This is really a group of components that make up one really big computer. And of course, any failure in any component during that time results in repeated work and lost effort. So like we have a system, Kalyan will explain checkpointing, where they can resume from where they last saved their state, but you can't do that all the time. Any failure requires the resumption from a checkpoint. So uptime is king. Any and every single failure can be incredibly costly. But also, user experience is equally high priority. The researchers that we're working with are some of the best in the world. They're the people pushing the state-of-the-art of AI forwards and minimizing the friction between them having an idea and then being able to get some test results. That's like one of the most important things we can do. Many of them have worked in high-performance computing environments before. They have a toolbox of common techniques that they want to reuse. And being able to allow our users to do things their way without enforcing that they will do things the way we would like them is almost as hard as the technical challenges in some ways. Giving people the opportunity to work in the most effective way for them is really important. So we want the highest possible performance compute with absolute flexibility and ease of use. Well, sounds easy, right? I'm going to hand you over to Kalyan for some specifics on.
As Chris introduced, what's special about AI training workloads? You must have gotten some feel for it, but let's zoom into large-scale training, which is the current state of the art with LLMs, ChatGPT, what have you, right? It's a totally different beast. At that scale, having powerful compute is not enough. Communication and storage also come squarely into focus, right? Let's take a look at how one of the Llama models was trained on this cluster. In fact, all of the Llama 2 models were trained on this cluster. You cannot fit the model on a single GPU, of course, not even on a single host with 8 GPUs. You have to scale up to 2,000 or 4,000 GPUs. At that point, every single factor comes into play in the cluster, how you design it, storage and communication. Everyone talks about GPUs, but let's spare a few minutes for communication, right? If you understand the training loop, there's a forward pass, backward pass, and upgrade in the gradients. The upgrading gradients is about exchanging information with all of the ranks. They're called ranks. You can call them workers. Each worker is running on a single GPU. Depending on the scale, and depending on the model architecture, different communication patterns are used. These are called types of parallelism, FSTP, data parallel, model parallel. There's a lot more to it, but I'll summarize this. Essentially, there is all-to-all, there is all-reducer, different communication patterns that come into play. And this itself can take up to 45% of your training loop. Each iteration, as much as half of the time is spent in communication. So you need a really fast and reliable interconnect. What's the other key underpinning for training is data. Without training data, there is nothing to learn from, right? Some of these large models use up to 2 trillion tokens. Each token is a word in language. How do you supply this data fast so that you can keep the GPUs busy? That's our goal. Your training data needs to be distributed in a way you can supply super fast to the nodes. I think I may have skipped one. Yeah, that sounds good. Cool. Let's look at RSE. This is actually a real picture from the cluster itself. A few numbers at the top line. The aggregate compute power is almost 5 exaflops. And we use a non-oversubscribed InfiniBand fabric in the entire cluster, composed of 3 data halls. And we have up to 500 petabytes of storage. At a high level, instead of the numbers, let's look at the themes. Really powerful GPUs, fast and flat interconnectivity on the back end, and keep the data-hungry trainers is equal to GPUs unblocked. They must be busy as much as possible. These are the 3 fundamental principles when it comes to designing the cluster. I'll reel off a few specific numbers. We have 16,000 GPUs in the cluster, all DGX A100, the latest at the time of generation, each one with 80 GB of HBM, high bandwidth memory. And this is likely one of the largest and longest. Longest is pretty interesting. We can talk offline about that. But this is the largest and longest known InfiniBand fabric in the world at the time we built. Probably it's still now. We have thousands of switches, almost 2,000 switches in the fabric. Tens of thousands of links. This matters to how you think about reliability. We can go into that later. We have 10 petabytes of flash storage. This is used for code and checkpoints. Training code, and the checkpoints which are produced during training need to reside somewhere. And they must be visible from any node in the cluster. Right. As I said before, in order to keep the trainers unblocked, it's not enough to have massive amounts of flash storage. You need to build a layer on top to serve almost as a caching service. You need to throw the training samples to individual GPUs. So we designed and built a purpose-built storage service called AirStore. We'll talk about that. And that provides you 6 Tbps cache bandwidth. Cool. I brought up storage to the fore because it's neglected in most of these cluster designs and discussions. This is a really cool system that our team came up with. It's called AirStore. Essentially, what's a good analogy is I think of Netflix or CDN for training data. There are these thousands of GPUs spread all across the cluster. They all want a different training sample. It's as if you're clicking on a YouTube video or a Netflix short. Sorry, YouTube short and a Netflix video, right? What AirStore does is we ingest the data into bulk storage, flash storage. Sorry, the data is resident in the cluster. Whenever the training job starts, you are querying these samples, individual training samples. AirStore uses heuristics to fetch, cache the training samples, and supply them to the GPU when they want it. We support different access patterns, iterative as well as random access. And that throughput is super important for how fast your trainers can go. And this is a whole different presentation and a paper. This is just one slide here, but it gives you an idea of what it took to support large-scale training. There's another aspect to storage. This ties into what Chris said earlier, really smooth user experience. We want to keep the researchers unblocked, apart from GPUs, right? Researchers are expensive and rare talent. They need to be able to get their code and checkpoints super fast. So literally POSIX layer. For that, we built 10 petabytes of flash storage. When the training is running, checkpoints are taken and saved to this NFS store. If your training job fails or for any reason interrupted and restarted, you can pick off from where you left, right? And you just go to the last successful checkpoint or a specific checkpoint that you care about and resume, keep going, right? Similarly, code. The code is available from all the nodes. There is no mental tax on the part of the researchers. Say, where is my code? What do I do next? Nothing at all. It's visible, universally mounted. And then the most interesting part is the fabric, which is where I have personally spent most of my time, last year especially, in stabilizing it. Let me take a few minutes. This is the InfiniBand fabric. And why do we need it? Fast exchange of gradients. As I said, after the backward pass, you need to exchange or unify the understanding of training across all the ranks. And that's where the backend network comes into play. We built a non-oversubscribed IB fabric. It's 2-level. You hop from a node to a TOR to spine, and then back down. Nothing else. And no path is oversubscribed at all. And each host has 8 GPUs and 8 HCAs, host channel adapters per host. Each one is 200 Gbps, bits per second each, right? And some of the cool features are we have adaptive routing, we have in-fabric compute. In-fabric compute is super cool optimization where you can offload some of the math to the network itself. There's a famous thing called all-reduce. The network itself can do the all-reduce for you and cut down the latency and improve your training performance. And one cool number, if any of you have trained, are familiar with all-reduce communication primitive, we get up to 192 Gbps of algo bandwidth. That is super close to the line rate of 200 Gbps. And this is the flagship number for how good the fabric is. We repeatedly mentioned the largest and longest. The longest fabric actually was a negative surprise for us. We didn't realize, oh, okay, you need to keep track of the length of the links. That has a role in how you, what optimizations you can do or not do. And we are incorporating that into our next set of designs. But the fabric is a very sensitive but a powerful beast. If you keep it healthy, it does the job for you, and you can whip out training steps super fast. Cool. I spoke breathlessly about the GPU storage and networking. Let's step away from the hardware layer onto how does the user land on this cluster? How do we offer the resources to them, right? That's where the control plane comes in. That's where the software comes in. Our control plane has a bunch of components. I'm not going to talk about all of them, but one key component, in fact, the nervous system / brain is the scheduler. Scheduler is your window into the world. The researchers submit jobs, their training jobs via the scheduler. It lands, finds placement, runs, gets evicted, right? Gets preempted, requeued, and all of that. So what scheduler do we use? In fact, Meta has very powerful schedulers in-house. We picked a HPC scheduler called Slurm, because it's specifically targeted, again, to keep user experience on the cluster. So Slurm is HPC, supports gang scheduling, supports queuing, prioritization, and whatnot. This is an illustrative diagram. You can request a 1 GPU job, or you can request an 8,000 GPU job. And Slurm places the nodes for you, places the job on the free nodes for you, queues it up, And based on the priority, can evict other jobs, and you get your placement. And if you are evicted and you're going to be requeued, you are supposed to consume from, you're supposed to resume from one of the checkpoints, which is on the NFS. And that's how the storage comes in with how we design the fabric, how we design AirStore. One unspoken theme here is, if you really think about it, we kept the cluster homogeneous. No node is special. No placement is special, which makes the user experience, the ease of use possible. You land your job no matter where in the cluster, and you resume, there's no difference. Essentially exactly the same experience from every node anywhere. And of course, we use Kerberos, DNS, NTP, Nagios for event health detection. Health detection is a major part of our job, figuring out which nodes are good and which nodes are bad. They keep failing all the time. Yeah, cool. So that's about the control plane and the services. Off to Chris for why is this not a joke?
Yeah, why is it hard? Well, HPC is somewhat different. Especially if you're used to working in Meta or OCP hardware. The hardware that we use for this cluster is very different to the standard open compute hardware that Meta uses everywhere else. We have GPUs for a start. We don't really have very many GPUs in prod. I mean, we have a bunch, but we don't use them in this way. We have completely different switches. We have completely different HCAs. We have completely different storage devices. Hell, even the physical dimensions of the rack are different. Our open compute racks are 21 inches wide. These are regular 19-inch racks. But it's also a whole bunch of different vendors. And many of these vendors will only support their devices and services on qualified platforms. Or they'll provide you with specific management tooling that's not always easily available. And you can't necessarily get the source to rebuild it yourself. So you have to use a system that they qualify. In fact, we built a custom OS. These new vendors led us to new systemic requirements, and they had new software requirements and decisions. Fortunately, we have a very good relationship with our vendors. They were very amenable to us kind of showing up and saying, I know the rest of HPC installs a cluster and then runs it and then leaves it. Well, we kind of want to keep it moving forwards. We want the latest OSs. We want the new stuff. So we run this custom operating system. It's built, tested, qualified by our vendor. It's based on CentOS Stream 9. There's a few user space additions, a little bit, mostly upstream kernel. The upstream kernel these days is pretty good for this. But we don't really run it as a stream. I did a big presentation on this at CentOS Dojo in October 2021. I'm sure you can find that if you want more details. But we basically work on the CentOS CI/CD platform, picking composes and iterating forward on stable composes periodically rather than just rolling forwards every night or every install. But some other challenges. Kalyan.
Yeah. There are some other challenges. Yes, as Chris mentioned, we had to work closely with vendors. As it happens, some of the problems that we witnessed were kind of new to the vendors themselves. For example, storage. We worked with one of the best storage vendors in the world, and they were surprised by how our workload pushes the boundaries for them. Right? They have their peak throughput IOPS numbers, but that was not really useful for us. Well, I'm underselling that, but when you have 4,000 GPUs all pounding the storage array at the same time and writing files, checkpoint files, under the same inode, or creating them, you have a slightly different code path being exercised. And we were hitting errors, right? And we had to closely work with them to debug. That inode gets busy, and the observability and the debugging needed a different path. Regular metrics didn't help there, right? And we had another use case. This is a real production bug that we run on the path to launch. Data is being ingested into the cluster while training is happening, right? And flash devices started underperforming or, in fact, failing over. We had to live debug and unblock it before the cluster launch. And it required extremely close cooperation with the storage vendor. We had to build different observability and tooling on our side so that we can stay on top of such a repeat occurrence.
Yeah, one of the things that we rapidly realized that it doesn't matter whether you want it to, P95, P99, P99.9, none of them are good enough. The way the components in RSC are coupled together, a single failure anywhere can cause problems, slowdowns, badness for a job running on the entire cluster. It really doesn't matter what your P99.9 file system write time is. If all 4,096 workers in the job have to block until they've all finished writing, the only thing that matters is the P100. They're all going to wait for that long anyway. There's nothing you can do about that. Kalyan has some math to explain all of this.
Yeah, you can gloss over this math, but I was really curious. People complain about reliability, or in fact, they say, hey, why is reliability a problem? People who come from production web services said, yeah, let me take a look at what would a 4096 job GPU will last, right? What's the uptime is. You're happy with your 5 nines for each component, so I did a hypothetical math. Let's assume only 10 components per worker, per GPU, right? And with 5 nines, your job will last only 3 days. Remember, Llama 2 style or ChatGPT 4 style models take maybe 8 weeks to train. And in a best case optimistic simplistic model, your job can stay up only 3 days. And this is super optimistic. I would say 3x overestimate. And that's how you need to flip your perspective on what the nines mean or don't mean.
Yeah, I've thought about this for a while, but maybe 5 nines isn't enough. To give it real numbers, just one failure in a 4096 worker job stops the entire job and triggers a restart. That's a 0.02% failure. The cluster's still achieving 99.98% success, but the cluster's also wasting many, many hours of GPU time every time the job has to resume from its last checkpoint. It's just not good. And failures multiply, right? Like everyone's been told this, everyone's heard this. I'd never really internalized this until working on this project, that even if every step in your chain is 5 nines reliable, you only need 10 steps in that chain before it's only 4 nines reliable. And high-performance computing usually has more steps in every chain, and it's also usually more sensitive to failures in those steps. So we had to really push things much harder.
Yeah. I have another war story from the InfiniBand fabric. As I said, I spent a lot of time on this, right? Some dirty facts from the fabric, right? Your fabric layout, the cable layout matters, the bend radius matters to whether the individual link is performing at the speed that you want, or it has errors. The temperatures, the operating temperature in the cluster matter, because we had to work through this and debug. Is the operating temperature right? Are we degrading links because of that? And all this had to be figured out while operating the cluster with workloads running on it. I want to quote one war story. We had to do a very safe config change recommended by our vendor, right? Super safe config change. It's management lanes going down from 3 to 2. Cool. We did that one Thursday morning, and everything went down in the cluster. All thousands of GPUs dead. And we panicked. We couldn't figure out, and we got on a call. They had no clue either. And eventually, after 2.5 hours, we figured out, oh, there's a retry loop. The subnet manager is bombing, and every link is retrying, timing out, retrying. And this cascade built up, and the subnet manager had a really long queue. It would never get out of it. We had to break it hard and undo the change. And again, this resulted in an observability change, both on their end as well as ours. And they said, yeah, we never saw the scale, and we didn't know that this could be a bad code path.
It's always the safe changes, isn't it?
Yeah.
Yeah, this was unknown territory. Even the vendors had never really built a network this big before. Things like we keep talking about it being the longest network. I've never worked in an environment where the speed of light through fiber is the limiting factor of the size of my network, because I require a certain number of nanosecond round trip, and it's like, wow, this is kind of insane. It was unknown territory in different ways. Very few people have ever trained models on 2,000 or 4,000 GPUs. Only a very small number of teams, maybe 3 or 4. We had no plan to follow. There isn't really a run book you can do. You can't just go Google this and be like, oh, that's how I do it, great. Things fail. Like, I know everyone here knows things fail, that's why you're here. But things fail all the time in a system this complicated. And it's this complicated and this kind of dependent on success. It's just a fact of life, and stuff goes wrong. Sometimes failures are related, sometimes they're independent. It's a really weird world to work in. This like, Kalyan posted something internally this week about how, maybe the tail is the head, and the long tail of unknowns has a huge impact on a large cluster. The easiest way to break that down is to start with the highest impact issues. Find the ones that are happening most often, find the ones that break things the worst, fix them, move on to the next one, work down the slope slowly. But sometimes when you have enough data about your systems to be able to identify these errors, I mean, ideally before they happen, but even after they've happened is fine. Having people go find, fix, repeat is great. And here's the rub. It doesn't matter what their job title is. You can be software engineers, you can be production engineers. It really doesn't matter. We can talk a little bit about this complexity explosion, and when I try and explain like why these things are hard. With an RDMA fabric, something that would usually be really simple, memset, like save the contents of a variable into memory. This might become an entire remote procedure call across the fabric. Very fast, but has to pass through a whole bunch of devices, an HCA, an optic, a leaf switch, an optic, a spine switch, an optic, a leaf switch, an optic, an HCA. And every single one of those optical translations includes a pair of transceivers at both ends. Hands up anybody else who can SSH into their network cables? At both the sender and receiver end? It's very strange. You think this sounds similar to like a regular data center microservice model, but people don't generally use microservices for the RAM that your software is running in, right? Like, we've used Memcache and Redis, but they're caches. If you were to try and use Memcache as the working memory for your application, how good a time do you think you'd have? We're kind of doing that all the time. There's so much more complexity associated once you bring RDMA and remote memory access. It's kind of crazy. Kalyan did some debugging on this.
Yeah. We had to, like I said, I think I'm going to spare you the details, but we had to find how optics fail. Is there a supply chain problem? Or is the cable layout is causing more failures? Or were they not even plugged? This is really physics. Some human going and plugging in the wrong way, and our cable swaps. Cable swaps cut 50% of your bandwidth. That was a stunning discovery we made. That was a very surprising discovery, and how you prevent it. You need better barcodes, better labeling, better human-to-machine translation when you are actually in the data center. Cool. One of the interesting software issues that we ran into was, guess what? My co-presenter, Chris, here finds a bug in AutoFS. I was like betting, hey, Chris, you must be wrong. There cannot be bugs in AutoFS.
I was betting that I was wrong. Like, the line of code that I found the bug in dates to 2006.
Yeah, this got exposed because of the concurrent nature of the workload. And Chris worked through 2 of these issues, and we are trying to upstream it.
Ian, if you're here, come find me afterwards, please.
Yeah, and we found bugs in Kerberos, KCM, and Slurm, Aux. There was a memory corruption we had to debug and upstream the fix. So as you can see, we are hitting some unexplored territory in terms of how the systems are put under pressure, and that exposes new bugs. But having talked through all the troubles and pains and what it took to build, let's see what we produced so far. This is just a selected subset of the models that got trained on this cluster, Llama, Llama 2. Llama 2 has been a sensational hit, right? And Seamless, this is a translation, cross-translation across a bunch of languages. Code Llama, if you hate Python and you want the machines to write code, Code Llama is for you. And Segment Anything is a super popular image segmentation model out of Meta. All these are open source models, and we are proud to have been, the oven behind the cake.
Cool. That's a great description. we were also navigating some uncharted waters with culture. Nobody really had any idea how to build or operate this cluster. We decided to start with 3 key principles. Throw out the playbook, be open-minded, be curious. There's no right way, there's no wrong way. Let's find an effective way and go forward with it. But also own the vertical. You don't need to separate layers between teams as early as possible. Like, have someone whose job it is to own the whole thing. Have a team whose job it is to own the whole thing, and know enough about each layer to be able to work with the people on that layer and help them debug their layer and so on. But most importantly was iterate, and iterate fast. Like, try something. If it doesn't work, great. Try something else. If it does work, great. Keep going. The team, ourselves, were new. We had a widely geographically dispersed team, around about 30 people, based everywhere from Dublin, Ireland, New York, Richmond, San Francisco, and California, Seattle, and the Pacific Northwest, and myself in Hawaii. Anyone keeping notes, that's, I think, 12 hours of time difference between everyone in our team, so nobody had a good meeting time. We formed the team in mid-2020, so we kind of had to be remote first from the beginning, which was not the way Facebook used to work. So we ended up having to learn a whole bunch of new things. It was a big shock. I'm sure it was for everyone else in this room. I'm really glad we got used to it. I'm really glad we got to do it. I'm really glad I see so many faces in the audience today. I think everyone's happy to be properly back.
Yeah, that seems like a large team, right? You might be thinking, is this an SRE setup? No, not really. We have software engineers like myself, and we have production engineers. That's the working title in Meta, like Chris, right? There is no explicit SRE team at all. There is no build and handover. It's continuous collaboration. How do we work together? I'm supposed to be SWE, and I work on the training loop, work closely with the researchers, and Chris and the PE team focus on infrastructure. They are the bridge to the vendors, the hardware, and the cluster, right?
No. That was never going to work. The PE team work with the researchers all the time. Kalyan and the SWE team work with the vendors all the time. I know Kalyan was on a call with a vendor late last night. It's really the joined up nature, the combined nature of our team is one of our biggest successes. And this isn't a first and second line relationship either. Both teams work hand in hand every day. Sometimes we find the problems, sometimes PE find the problems. Sometimes PE fix the problems, sometimes we fix the problems. That's really not the point. And I was talking about this with my team last week, talking about making this presentation with my team last week, and this is a direct quote from a guy on my team who said, "I keep forgetting they're technically a different team. Yeah, I'm really glad we get to work so closely together. I couldn't imagine doing this without that relationship." And I think the fact that even relatively new folks on my team are like so excited about working in this way is kind of telling. I think the key point is that SRE isn't something you do. It's something you do, not something you are. You can be anyone doing SRE. It doesn't matter what your job title is. Like, our team are kind of all SRE, even though none of us are really SRE. And I think I'd like to encourage people not to be afraid to kind of branch out and work on reliability things, even if it's not necessarily 100% your job, even if it's not necessarily in your job title. I think it's really important people feel empowered to solve reliability problems and to work on reliability issues, whether or not it's necessarily broadcast out there. And with that, thanks to a whole bunch of people, a whole bunch of people on the SWE team, a whole bunch of people on the PE team. We've worked with so many researchers and cross-functional partners, various vendors. I'm sure they'll all name us eventually. Thanks to our leadership team. They've let us do this. It's kind of a crazy bet to begin with, but they seem to be happy with us.
Yeah. Cool. I don't believe we have time for questions.